Okay. Assalamualaikum warahmatullahi wabarakatuh. This is example for plane truss problem for stiffness method. This example is taken from the given examples in ECS 555. Okay, so when you first given the plane truss problem, to do the stiffness method, what you first need to do is to labeling or numbering the node. So as you can see here, you have 1, 2 and 3 members, so you need to number them. Okay, it's not the numbering is not fixed. You can number them as what you like, but in these examples the numbering is, this is node 1 and this is node 2, which is node 1 and node 2 develop the member 1, and for member 2 it is developed by node 1 and node 3. For member 3 it is developed by node 1 and node 4. Okay, and here some notes for you. Truss element, bear in your mind, it has 2 degrees of freedoms for planar truss problem, where you have displacement and force. Okay, and another note is that angle is measured from x-axis. So in this case, this is your x-axis, this is your y-axis. So the angle is measured from x to the member. Okay, so in this case, for member 2, which is governed by node 1 and node 3, the angle is 45 degrees, and it is positive because counterclockwise is positive measured from x-axis. Okay, if you look at the derivations in these equations, measured from x-axis to the member that we determine, it is positive. Step 2 is to determine element member stiffness. The question is, how are you going to determine the element member stiffness? For truss, the element member stiffness is given by these equations, meaning that the K stiffness, K is represent the stiffness, equivalent to area multiplied by the modulus of elasticity divided by the length of the member of the truss, and here is the derivations from the formulations given in your notes. So you have c squared, c means cos theta, s means sine theta. Okay, now let's look at element number 1. So just to recall, element number 1 is governed by node 1 and node 2. Okay, so if you look here, node 1, node 2, element number 1, and the degree of freedoms, as I highlight here, you have u1 v1, u2 and v2, meaning that for truss you only have 2 degrees of freedoms at the nodes. So in this case, if you look here, for node 1 u1 v1, node 2 you have u2 v2. To do that, okay, so you need to write the stiffness, okay, according to these equations. So at the moment you are doing for element 1, so local element 1, K1. So for local element 1, alright, so you have u1 v1 u2 v2. Why you have u1 v1 u2 v2? Because here is the nodes, here is the degree of freedoms of your element. So here you have u1 v1 u2 v2. So you have u1 v1 u2 v2, and this one also symmetry u1 v1 u2 and v2. So for this, why you get it 0? Because you need to look at the angles. Okay, for member 1, as I said in these notes, angle is measured from x-axis, counterclockwise is positive. In this case, from x measured to member 1 is 90 degree. So for 90 degree, okay, 90 degree, now you can calculate cos 90. What did you get for cos 90? Cos 90, you get 0. And what are the elements that you need here? Sine, okay, sine 90. So sine 90 is 1. And if you have this one is cosine, okay, cos 90 times with sine 90, and because one of it is 0, therefore we get 0 here. So having that 0 and 1, okay, so that's why you have this. Okay, just to recall, okay, just to recall here, cos squared, which means 0, okay, so that's why you get 0. And then this one also 0, this one also 0, here also 0, and here is 0 as well because you have cosine, and here you get 1. Why you get 1? Because you get sine 90, which is 1, therefore you get 1. And similarly goes to the rest of the matrices, which is fulfilling these equations. So you have to do these truss formulations to determine the local element stiffness for all these 3 members. Okay, member 1, member 2, and member 3. At the moment, the one that I have shown it to you is for element 1, and this is the stiffness matrix for local element 1. And 5 times 10 to the power of 5 is calculated based on the examples given in these questions, where you calculate A times E over L. And that's why when you calculate that, refer to the example, you get 5 times 10 to the power of 5. Okay, now let's look at element 2. Element 2 is located 45 degrees from x-axis, which is this is element member 2, 45 degrees from the x-axis. And because 45 degrees, therefore you have cos 45. Okay, so cos 45 and sine 45, both you get 1. Okay, cos 45, sorry, 0.707, and here is z similarly, okay, you will get 0.7071. So you get both 0.7071. So once you get 0.7071, okay, in which is equivalent to square root 2 over 2. Okay, so why, if you look at the examples, it gives you square root 2 over 2 because it want to have the element, okay, the element inside the matrices here equals to 1. So what in the example, what it has done, okay, so the multiplications of the examples, if you look here, as you can see, okay, in these examples you will get 176.78, and here is 1 1 negative 1 negative 1, because of you already has multiply with square root 2 here. Okay, this is for area, this is the Young's modulus, and this is the length. So instead of using into a decimal form, it make it in terms of the fraction point forms. So here, if you divide, you multiply back here with 2 inch, okay, with 2 inch, and then you will get 1 inside here. Okay, so therefore you get 1 1 negative 1 negative 1. And how you get those is similarly by having all these formulations. It's just that in this case, okay, it just multiply with 2 so that you can have a round number inside the, what we call this, inside the matrices. Okay, so once you get for element number 2, now you can go for element number 3. In element number 3, okay, if you refer to your examples, element number 3, so x is measured to the element, definitely no degree or no rotation angle in that particular element, therefore the angles is 0. So when the angles is 0, okay, when the angles is 0, it means that cos 0 equals to, and sine 0 is equals to, so in this case cos 0 equals to 0. Okay, cos 0 equals to 1, and then you get sine 0 equals to 0. So once you get cos 0 sine 0, insert in this equation for element number 3, therefore you get 1 0 negative 1 0, and here you get 5 times 10 to the power of 5 because of your AE times L. Okay, so you get 5 times to 10 to the power of 5. Okay, so once you get all these elements, local element stiffness, which means this is for element 1, and you have element 2 stiffness, and then you have element 3 stiffness. So once you get all these element stiffness, you need to assemble them into a global stiffness matrix. So the global stiffness matrix, how you're going to get the global stiffness matrix is, you need to merge all the elements by writing here. Okay, you have u1 v1 u2 v2, okay, and then you have u3 v3. Why? Because you have here u1 v1 u2 v2, okay, and then you have here u2 v3, sorry, u3 v3, and then here you have u3 u4 v4. So you have 1 2 3 4. Okay, so since you have 4 nodes, therefore you have at each node you have 2 degree of freedoms. So therefore your global matrix will be 2 times 4, which means 8 times 8. So here you have u1 v1 u2 v2 u3 v3 u4 v4, and then here you have u1 v1 u2 v2 u3 v3 u4 and v4. So it is 8 times 8 matrix. Okay, okay, now is the time for you to determine the global stiffness matrix. To determine the global stiffness matrix, there are 2 ways. Okay, because in these examples, the problem with this example is that you don't have a similar factorize in your all local element member. For instance, if you look here, element 1, the K factor is 5 times 10 to the power of 5. While if you look at element 2, the authorized K factor is 176.78. And meanwhile, if you look at element number 3, is 5 times 10 to the power of 5. So meaning that when you wanted to add them up in the global stiffness metric, there are two ways. First, you don't need to have the same factor for all element. Okay, you don't need to have the same factor for all element. So what you can do, okay, the first way is, okay, what I said, the first way, no need to simplify so that you get the same factor for your stiffness. So in this case, you need to find what is the value here. Okay, so in this value, okay, you have u1. Okay, so row 1 column 1. So for row 1 column 1, okay, row 1 column 1, you need to go back and look at all your member stiffness. So in this case, you have three local element member stiffness. So here you can see for element number 1, so you have u1, which is 0. So you don't need to add them up from element number 1. And now looks at element number 2. So element number 2, you have u1, which is 1. Okay, 1. So meaning that here you get from element number 2 u1 and u1, which is 176.78 times 10 to the power of 3 times 1, which is this one, times 1, plus, okay, plus, look at element number 3. Okay, element number 3, you have u1 and u1. Okay, so 5 times 10 to the power of 5 times 1. So here you get 5 times 10 to the power of 5 times 1. So therefore you get 676,780. So because you only have 3 members, so and element number 1, the coordinate for u1 and u1 is 0, so you can ignore this. Therefore, the global stiffness matrix you can fill up for coordinate u1, u1, okay, is 6780. Okay, let's now try for coordinate u1 and v1. Okay, so let's look at u1, v1. So first look at your first element member, element number 1, u1, v1, 0. Okay, so meaning that for element here, okay, column row 1 u1, okay, so 176.78 times 10 to the power of 3 times 1. Okay, just a second, let me write it up. So u1, v1, 0. Okay, 0 plus, let's look at number 2, u1, v1 is 1. So 1 times with the factor out there, 176. So plus coordinate here, 176.78 times 10 to the power of 3 times 1 plus, okay, plus, look at your element number 3. Okay, element number 3, u1, v1. So here this is 0. So 5 times 0, you will get 0. So 5 times 10 to the power of 5 times 0, you will get 0. So finally, for this coordinate, okay, which is u1, v1, you will get 176,780, which is come from these equations. Okay, now let's look at one more examples. Let's take for global stiffness matrix, and actually similar approach you will go for the rest of these examples. Okay, for the rest of these examples. Okay, now let's look one more. Let's say you have u2. Okay, let's say you want to find at this member. So u2, u2. Okay, so u2 and u2 here. u2, u2. So u2, let's look at first member element. u2, u2, 0, so not affected from element number 1. Let's look at element number 2. Do you have u2 in element number 2? You don't have, because you only have u1, v1 and u3 and v3. So now let's look at here. Do you have u2? You don't have u2 as well. Okay, because you only have u1, v1, u4 and v4. So meaning that for the conditions here, u2 and u2, it is 0. Okay, so as I mentioned earlier, you have two ways. The first one, because your factor for K stiffness are not the same, okay, for element number 1, element number 2 and element number 3, they are not the same. Easiest way, just add them up as it is and you will get like a biggest number like here. Otherwise, if you wanted to make it simplified by having the same factor overall, okay, what you can do is by changing the factor, instead of having 176.78, change this into 5 times 10 to the power of 5, so that you can have the similar factor for K value for element number 1, element number 2, okay, and element number 3. So how to make it factorized and simplified so that it can give the same factor? So you can look here for simplification factor. Okay, so rewrite element 2 so that the factor became 5 times 10 to the power of 5. So how you wanted to make sure it get 5 times to 10 to the power of 5? So the original factor is 176.78 times 10 to the power of 3. To get the same factorized, you need to multiply with 5 divided by the original, and then again multiply with 176.78 times 5, so that this actually it is become 1. So because the objective is we wanted to make sure that we can get the same factorized here. Okay, in that case, here and here you can cancel up. Okay, so cancel up is become 1. So in here, this factor, okay, you multiply with 1. So when you multiply this with 1, you will get inside is 0.354. So then this divided by this is equals to 1. So therefore you get factor 5 times 10 to the power of 5. So when you get 0.354, 0.354, and here, okay, is this will be negative 0.354, negative 0.354, 0.354, negative 0.354, and the rest. So the same way you can determine for your element member stiffness. Okay, now let's using the same factor. Okay, now u1, u1. Okay, actually you need to have another u3, v3, u4, v4. I mixed them up and add them here. u4, v4. Okay, so now let's find what is the element numbers here for u1, u1. Okay, let's look at the first element. So now our factor out there is the same, 5 times 10 to the power of 5. Okay, so with the same factor all overall, So let's look at element number 1. Element number 1, okay, u1 and u1 is 0. Okay, so here is 0 from element number 1 plus, okay, plus, let's look at element number 2, which is here. Okay, you have u1 and u1 0.354, okay, plus 0.354, and then let's look at element number 3. Element number 3, you have u1 and u1 is 1, so plus with 1, so in total you get 1.354. So here is 1.354. Let's try at v1 v1. Okay, again you go for element number 1, v1 and v1, which is 1. Okay, so 1 plus, looks at element number 2, this is element number 2, v1 0.354, so plus 0.354, and then looks at your element number 3. Element number 3, v1 is 0, so plus 0, so again you will get 1.354. so here is 1.354. okay, so here is 1.354, here also 1.354, and the same way you have to do for the rest coordinate in these matrices.